Welcome to the third instructional video for 7th grade math at Krista McAuliffe Academy in the fall of 2018. This video covers the main concepts and terms of our third unit titled Proportionality. As with our first two instructional videos, students should use the Cornell closed notes provided by the teacher while they watch the video, filling in the missing word or words. After filling in the missing information, students should write a question for each box or chunk of information that will help them connect with the key concept or terms in that box. The day after taking the notes and writing the questions, the student should answer each question using complete sentences in the summary section of the Cornell notes. This is Module 1, Topic 3, titled Proportionality. Our learning objectives. Students will recognize and represent proportional relationships between quantities using tables, graphs, and equations. Students will identify the constant of proportionality in tables, graphs, and equations. Also in diagrams and verbal descriptions of proportional relationships. The math standard is 7RP, which is to analyze proportional relationships and use them to solve real-world problems. Why we are learning this, proportionality is just a fancy name for the multiplicative relationships that shape our world. If one bag of chips costs $1.25, then 2 bags of chips cost twice as much. Being able to recognize and represent proportional relationships in different ways allows us to broaden our understanding of the world we live in and increase our ability to communicate what we know with others. How will we know if we are successful? We will know we have achieved the math standard if we can identify and interpret the constant of proportionality in relationships between two quantities as presented in tables of values, graphs, equations, and in words. First, what is a proportional relationship? A proportional relationship is a multiplicative relationship between the amounts of two different things. For example, every soda costs 75 cents. There is a proportional relationship between the number of sodas and the cost in dollars. Why X and Y's? We are going to be starting to look at more X and Y in this unit. And the question is always why? Why do we need X? Why do we need Y? Well, because we live in a big world where individuals and companies net thousands and millions and billions of dollars over the course of 1 year, it helps to think beyond whether we have enough change in our pocket for one soda or two. It helps to think about how much things cost over the course of the year, and inversely, how much somebody else is making off our 75-cent soda purchases over the course of time. Well, never fear, algebra is here. We can define variables like x and y to represent the number of sodas and the cost in dollars. We can make tables of values to show the xy coordinate pairs and write equations to generalize the data. What are x and y? X and Y are variables used to represent the amounts of two different things that are related. In general, the amount of one thing, which is going to be our Y variable, depends upon the amount of the other thing, which will be our X variable. X and Y are coordinate pairs, and we see it written in parentheses X comma Y. And each pair is held together like a married couple that never gets divorced. So X and Y don't exist independently when we are talking about a mathematical relationship between X and Y. What we have are XY coordinate pairs that stick together like glue. What does X represent? What does Y represent? You will be asked that again and again. Well, in general, X can represent anything and Y can represent anything. So sometimes you'll see X and Y without any sort of verbal description. But if you're asked this question, it's telling you that you need to look at the words in the table, on the graph, or in the paragraph, sentence to try and figure out because X and Y are going to represent something in the real world. So, in our given situation, every soda costs 75 cents. What we're going to do is let X represent the number of sodas, and we're going to let Y represent the total cost in dollars, because Y is our dependent variable, and the total cost in dollars does depend upon the number of sodas that we buy. What we have here on the left side of the screen is four sets of XY coordinate pairs in a table. And always in a table, you want to look at the heading. So it says X is our number of sodas and Y is our cost in dollars. And we have our first pair, which is 1 and 0.75 or 75 hundredths of a dollar, which is 75 cents. So we know that one soda costs 75 cents. Our second pair is our 2 and our 1.5 or 150. 3 and 225 is our third coordinate pair. And then the fourth one in the table is 20 sodas, which would be $15. Sometimes we'll see the XY coordinate pairs in a table like we have here on the left, but we'll also see them written like this. And this is kind of our cue that they're going to be graphed, but there's no difference in what they tell us. They are still telling us the XY pairs, the way they pair together, what those numbers are. One question you'll be asked to answer in this unit is how do we check for proportionality in tables? Well, for every coordinate pair, y over x or y divided by x, every coordinate pair always has the same value. So what we see in this diagram here is we have our pairs from the previous slide, 1 and 0.75, 2 and 1.5, 3 and 2.25, 20 and 15. And then just to the side of each row, you'll see y over x, and it's set equal to the values in the table. So we have substituted in 0.75 for y and 1 for x. In the second row, we have 1.5 over 2. In the third row, we have 2.25 over 3, and then 15 over 20. All four of these are equivalent ratios, and this is a way that we can test to see whether or not a table of values is indeed proportional, is we can write y over x, y over x, y over x, y over x, substitute in the actual values from the table, and then type them into our calculator and evaluate. If we get the same number for each one, then we know we have a proportional relationship. What is the constant of proportionality? Constant of proportionality is going to be one of your big buzzwords in math this year. And it is the constant multiplier or the constant of proportionality that we multiply each xy to get our y. So the constant of proportionality is the ratio of each y value to its corresponding x value. It is the unit rate for the situation, and it is the value of y when x is 1. We have here in the box on the right an equation that says k, or our constant of proportionality, is equal to our y value divided by our x value. In terms of the situation that we were looking at, what is the constant of proportionality, k, for the cost of sodas to the number of sodas? Well, we can see in the table, I've kind of lined it up here. If we have one soda, we multiply that by 0.75 and we get the cost of the soda. And the same thing happens for if we have two sodas. We multiply by that cost and we get our $1.50. So 0.75 not only is the unit rate for cost of soda, it is also K, our constant multiplier in the situation. So in our situation, K is 0.75. It's also the cost of one soda. We're going to use K in our equation for proportional relationships because y is always x multiplied by a constant number. We can write that equation as y equals k times x. In this equation, x is a variable that represents the independent quantity. Y is also a variable. It represents the dependent quantity. K is not a variable. K is a constant. And the reason that we use a letter to represent it is because it follows this sort of parallel construction. So K is not a variable. K is the constant, and we find it by dividing each y value by the x value in a certain situation. You will be asked to use equations to answer questions and generate tables of XY coordinate pairs. So what we have here on this slide is an example of using our equation y equals 0.75 times x, because x is the number of sodas and y is the total cost. And it shows three examples of substituting values in for x to get the corresponding values of y. And on the far left, our first example, notice it shows the same steps that we've been using so far this year. Step 1 just rewrites the equation, y equals 0.75 times x. In the second line underneath, we see the substitution. We substituted in 0 for x, so now the equation says y equals 0.75 times 0. In the third row underneath that, I have evaluated that number times 0 equals 0. What I have found is the y value that pairs up with the x value that I inserted into the equation. So what I have is the coordinate pair 0, 0. And what that means is that 0 sodas cost $0. In this second example here in the center, the substitution is for one soda. So the second line says 0.75 times 1. When you evaluate, you get 75 cents. And what I have found is another coordinate pair, XY coordinate pair. If I buy one soda, it costs 75 cents. On the right, we have our third example. Same step 1, rewrite the equation. Step 2, I substituted in for 10 sodas. When I type that into my calculator or do that math in my head, I get $7.50, which is how much 10 sodas cost. from this process, we now have three XY coordinate pairs that have specific meaning for the problem situation. We will also be graphing proportional relationships. And what you want to think about are what are the key features of a graph of a proportional relationship. I have graphed the relationship that we've been talking about in this video, which has to do with the cost of sodas, how it relates to the number that we buy. What we have is a dot at 0, 0, which means that when I buy 0 sodas, it costs me $0. And then my second dot is at 1 and 0.75. So what I did was I slid, I'd like to show you, okay, here we go. So I started here at 0, I slid over to 1 because that's my x value, and then it says 0.75, which is 3/4 of 1. So I didn't slide too far up. I stopped right here about 3/4 of the way to the line that is y equals 1, and I made that dot. For 2 sodas costing $1.50 or 1.5, I slid out here to 2 on the x-axis, and then I slid up to 1.5, which is halfway between 1 and 2 on the y-axis, and I made that dot. And my last coordinate pair I plotted was 10. So I slid over to 10 on the x-axis, and then I slid up to 7.5, which is halfway between 7 and 8, and I made a dot there. Then I took a ruler and I dotted the line that connects all these dots. What we have are three key features. One is a straight line, and it has to pass through 0, 0 for it to be proportional. So one thing that we could make note of is that our XY coordinate pairs, when we have a proportional relationship, they're going to make a straight line that goes through 0, 0, which is our origin. Another thing that we can make note of is that we can find our K, our unit rate, if we take a look at the value of y when x equals 1. So right there, now I plotted it as 1 comma 0.75, so we already knew that value. But if we didn't, and we had a graph, we could just eyeball it, and we could come over here to where our x value was 1, and then just slide up to where we found our dot, and slide over to the left-hand side and see how much our value is. All right, the last question is just what is direct variation? Direct variation is a math buzzword, and it's just the same thing as proportionality. It means the same thing, but what you'll get is sentences that talk about y being proportional to x, and you'll also get sentences that talk about y varying directly with x, and it means the same thing. So if we have a proportional multiplicative relationship between two quantities, we can conclude three things. We can conclude that y varies directly with x, and you will see that on your test. You will see that. Yes, you will, and you'll want to know what it means. So varies directly, and then also y is proportional to x. We can also conclude that y is going to be equal to some constant number times x. So in conclusion, proportionality, also known as direct variation, can be recognized and represented in tables of xy coordinate pairs, graphs of xy coordinate pairs, equations in the form of y equals some constant number times x, and also just in words and verbal descriptions that reveal the constant multiplier that exists between two quantities that are proportional.